Today we're going to be talking about switches. So I've been getting to play around with making my own little version of Pink Floyd's Laser Light Show here. We'll get to messing with those later. Also built this really overcomplicated switch right here. So we'll get to play with that later too. But to get started, first we're just going to talk about the most basic circuit possible, which is a power source. So right here I'm using one of our regular batteries. This came off of Springwoods High School out of their old demoed panels, so I get to use it for fun stuff like this. And I've just got my negative wire connecting all the way. This is a light for a trailer that I picked up from O'Reilly's. And then I get my positive wire, and I made a little connection point so I can just quickly slip that in. And you see, this is a circuit. It's complete, it works. It starts at the battery. The electrons get forced out by the energy going. And as soon as they're forced out here, they want to return back into the battery, but they're not allowed to go backwards. So they have to go through the circuit all the way across. The energy from those electrons moving is what's producing our light right here. And it comes back through and returns to the battery. Electricity, that's how electricity works. It's always seeking to get back to its source. So that's like in our safety talk, how we talked about the path of least resistance. It's looking for the fastest and easiest way to get back. And so that's why electrocutions happen and things like that. It's also how different branches of circuits work differently. So if we want to do more with this circuit than just have this light be on all the time, we have to start introducing more things in. So like I said, this is the world's simplest circuit because you have your power source, your positive side of the circuit, the thing being activated by the power, and then it returning. So only really one component besides that. If we want to turn it off, any point in the circuit, we can break it. We could cut the wire right here. I'm going to kind of simulate that by just unplugging these. It's surprisingly good. So see, the light turned off because I unplugged it on the positive side. I could undo this wire nut on the negative side and it would turn off. I can disconnect it from the battery on the negative side or disconnect it from the battery on the positive side. So anywhere in the circuit that you cause an open makes the light turn off. But we don't want customers, we don't want people, we don't want even you and I to have to go and mess with bare wires all the time. In this case, it's okay because it's just a little 12-volt battery and it's got an easy path to ground right there, so it's not shocking me at all. But if we want to do more with it than that, we need a way to control it. And so that's where this comes in right here. And this that I built is the main, kind of the centered thing of what we're going to be working with today is these three commonly used terminals, the normally open, the common, and the normally closed terminals. We use them for stuff all the time, whether it's fire alarm, security, even intercom sound stuff uses it when they have like override relays and stuff. So it doesn't really even matter which part of the circuit you're working on. You're going to be dealing with these style terminals, and even basic light switches in houses use it. So anything dealing with electricity is going to deal with this. So it's really fundamental that we get a good grasp on what these three terminals are for. So just a brief description of kind of how it works. First, I have my toggle switch right here. So I'm going to be referring to resting state, and that's when this toggle switch is down, and you see this in the normally open and normally closed. That normal is referring to when the switch is in its resting state. This contact is closed, this contact is open. Whenever I take it out of the resting state, then it's no longer, they reverse. So resting state is what these labels say, not resting state is not what they say. So to give you a visual example of that, I'm going to take this light right here, and I'm going to put it in this terminal right here on my normally closed contact. And I'm going to take the positive from the battery, and I'm going to connect it right here to my common. So now you see my light has come back on, because I've now closed the circuit. This is the same as if I took this red wire and attached it right here, these two together. Because inside this switch, those two are connected. Now, if I take it out of its resting state, you see the light goes away because the closed terminal is no longer closed. It's now open because we've taken it out of that resting state. And then I'm going to hook another light up here real quick so you can see that it forced the normally open contact into that state. So I have this amber light here. So all I have going on with this negative side of the circuit, the negative leg comes from the battery and hits this where it T-taps, one to the red light, one to the amber light. And then if I put it in its resting state, that red light comes back on because the red light is connected to normally closed. And then the yellow light or amber light is connected to that normally open. So it turned off because its contact is now open. But take it out of resting state and it reverses. That's the really, really basic functions of these switches. So I guess my first question is, everybody got that? Everybody following along with me? Does that make sense? Is everybody ready for me to keep moving?
Get on with it.
All right. Okay. So I want to explain why I did a couple things real quick. So I attached my positive to my common. I like to always do that anytime I'm working with switching a circuit on and off, because then no matter which way I put the switch, it's going to turn on one of the sides of the circuit. If I took this positive and I connected it over here to my normally open, this normally closed terminal will never come on because normally open and normally closed are never associated with each other. They never have a connection all the way through. But if I were to flip it up into the off normal state, take it out of its resting state, normally open is then connected to common, and then something would work. Whereas if I keep my power connected right here to my common and I flip it up, this one works. I flip it down, this one works. So that's the first thing I like to do, because then no matter what I'm working on, it's going to work. And then I just pick which side of the circuit I need based on what my function is. So then over here, I have my negative. I'm going to take that light away just to simplify this again. The negative side of my light goes straight to the battery. You don't ever want to connect your positive and your negative to the same switch, because then whenever you switch into whichever position you hooked it up to, for instance, if I was to land this negative right here to the normally closed terminal, anytime this is in resting state, it would actually cause a direct short. That would kill the power, has the chance of overheating, doing something bad to the battery. It can damage the battery. It can actually cause the battery to explode. If you're working with a control panel, it can cause the control panel to short out or have some kind of problem that way. So you don't take both sides of your circuit to your switch. So I always take my positive side to it, so I switch the positive, which means I take the negative side straight to my device. So right now, I'm going to pretend this is a water flow bell. I know it's a red light, but right now our red light is actually a water flow bell, and this switch is a water flow switch. So there's two ways we can activate a water flow switch. One would be, like we showed earlier, where we take our positive and our negative straight to the bell, and then we use programming in the panel to turn it on and off. This isn't smart enough to get programmed at all. So I have to introduce a switch. Right, we have the common right here. Like I said, I always bring my power in on my common. And then I have to pick, okay, do I want my bell to always ring and then stop when it goes into alarm, when the water flow goes into alarm? Or do I want it to not normally ring and then only ring when it's in alarm? And since the function of a water flow bell is to ring when water is flowing, that tells me that I only want it to ring whenever it's in alarm. So I'm going to put it on normally open. So there's normally not any kind of closure between the circuit. The light is normally off. The bell is normally not ringing. And then whenever water does start flowing and it goes into its alarm state, it leaves its resting state, then the bell starts ringing. And then whenever the water stops flowing and the paddle in there comes back down, the bell turns back off. So that is how the normally open contact works. There's going to be any time that you have anytime you have something that you only want to activate, you only want to do a particular job, whenever it's an alarm, you're going to trip it with the common and normally open contacts. Now, if you think about another function we do that we very regularly use normally closed for, I'm going to talk about air handler shutdown. The customer normally wants their air conditioner on, so you would want to put that in normally closed. So this light is now representing that the air conditioner is on. So you see I still have my negative going over to my battery and my positive going over here to common, but just by moving from normally open to normally closed, it turns it on all the time. So my air conditioner is always running, but then some smoke gets in the air duct. That duct detector goes into alarm and it turns the air conditioner off. So now we're not spreading smoke through the building. So that's going to be an example of when we use the normally closed. So sprinkler bells are going to be that normally open. Air conditioners are going to be that normally closed because they normally want the circuit complete. They normally want the air conditioner running. Is everyone still with me?
Yeah, so does that work for the doors and the monitoring of audio system? Same thing?
Yeah, okay. So I'll get into how the security contacts for doors work in a second, because I'm going to bring my meter over here, and instead of using the light and the battery, we're going to use the meter and have a resistor. But as far as door locks go, particularly on our fire alarm side, we have our pull station that we put in a special switch that adds two sides of the circuit. One side will tie to the pull station. The other side will actually tie to the Maglock. Over the next couple of weeks, I'm going to keep talking about this same topic, but I'm going to have the actual fire alarm parts in front of me. So I'll get a conventional duct detector, and we'll go through how to wire up the normally open, normally closed, and normal and common terminals, and for supervising troubles and supervising alarms on those conventional duct detectors. I'll try to get some stuff for how to wire up a Maglock. I'm working on getting some stuff so we can wire up like that sprinkler flow switch I was just talking about. It'll wire the same way as what we're showing here, but you'll get to see it on the actual device. I'm trying to ease back into this and kind of get us going and get the general concept down. And then we'll keep making it more and more specific as we keep going. So for a Maglock, they normally want the lock to be locked, and then they want the pull station to be able to unlock it. So in that case, you would want it in its resting state. You would want it to be on. And then whenever that pull station is pulled, it goes into its alarm state. That lock becomes unlocked and people can get out of the building. And then here, I'll go ahead and get rid of this stuff. The only thing that'll stay is the switch, and I'll show you the other part of the doors, like with the door contacts and how we supervise things like that. So got my meter and a bunch of tangled wires. Okay. All right. So I'm going to start. I'm using these alligator clips to help me hold things. Normally, things would be cut and wire nutted the way we normally do it in the field. So I'm connecting my black to my common. When you're using these switches this way, when we're the ones doing the supervising, whether it's for security systems or it's for using a monitor module to monitor sprinkler equipment or whatever, they're not polarity sensitive. You can put black to common or red to common, or in the case of the monitor modules, you have a yellow and a purple lead. You can put yellow or purple to common. And then the other side is you're going to have to determine what you're looking for. So is your switch or your relay that you're monitoring normally going to be turned on or turned off? So I'm going to assume that we're watching a door contact, like for a security system. So if I do that, I'm going to use normally open. And let me put this over here. So you can see right now that you can see 46 K ohms. I'll hold the meter up. Maybe that'll pick it up a little bit better. You have that 46 K ohms right there. So I'm seeing my resistor from common to normally open. So everything is all well and good. And then I flip my switch, and then I get this short. I don't know why I said this is for a security door contact. This would be a better example for sprinkler monitoring. So we'll switch that up. We'll say we're monitoring that water flow. So now that I see that short, that's going to tell my panel I have an alarm condition. And then whenever the water stops flowing, just like it turned that bell off, we go back to seeing the resistor. Because what's happening now, our power is starting in the meter, and the meter is taking the place of a monitor module, and it's coming out, it's coming down, it's hitting here, and then it's looking for the path of least resistance to get back to the meter. And so since this is open, it can't go through the switch to get back to the common because it's open, there's no connection there. So instead, it travels across this resistor and then gets picked up by the black leads to be brought back into the meter. So we're seeing the resistor because it's being forced through the resistor. And then whenever we do create a connection, the reason we see that short is because it is easier for the electricity to go through the switch that has no resistance than it is to go through the resistor, which has 47,000 ohms of resistance, as opposed to the 1.7 ohm we're seeing through the switch. So electricity is lazy. Electricity will always take the path of least resistance. It's going to work smarter, not harder, however you want to say that. So whenever there is a short available, when there is a way for it to get back faster, it will take it. And that's how these switches are working. That's how we're utilizing that normally open and that common. They're a little washed out, so I'm letting you see it a little better now. You can see I have this alligator clip here holding my resistor onto this terminal, and the other alligator clip is holding it onto that one. And you're able to see that there. And then whenever I flip the switch down, now there's no more connection. Clips are still all the same, but you have your you see your resistor. So this is how anything with any kind of switch that you're monitoring is going to work. The question between normally open and normally closed at this point comes down to what are you monitoring and how's it being used. So an MR101 style relay, and I'll have one of these because one of the other things I want to look at wiring up is elevator shunt trip. So while we're doing switches and relays and stuff, one of the days we'll talk about those elevator shunts. So I'll have an MR101 relay to show y'all then. In that particular instance, your relay is actually always powered, which means it's always out of resting state, because resting state is how it sits in my hand if I pull it out of a box. And then as soon as I apply power to it, it goes in, it's not resting state, it goes in the abnormal state. So in that case, whenever we wire up our monitor module to watch that, then we're actually going to use common and normally closed because it is usually powered. So the normally closed will not be closed. And then whenever it loses power, it returns to resting state, and we get our supervisory condition telling us that it's lost power. When power is restored, it goes back to its normal condition where it sees the resistor instead of the short. I'll get into door contacts like the security stuff on another time when I'll actually have a security door contact here, because those work kind of similar to relays. So I'm going to wait till we get into that a little bit more to get into those. But there's a magnet that actually pulls a switch over, and it's very similar to this concept, but it doesn't have all three terminals. Security contacts typically only have two terminals. And so you just put, one side in one and the other in the other. You don't have a choice to make. Whereas with the duct detectors and the sprinkler equipment, those you'll have normally open, common, and normally closed, so that whatever it is you're trying to do with them, you can do. Does that answer your question well enough till we actually pull out some security parts and pieces? And does anyone else have any questions? Or Ramsey, do you have any more questions either?
Oh man, I do apologize. Sitting up here talking with Mark. So the last 2 seconds of that I didn't get. I'm gonna see if I can hit my replay button.
Okay. Well, I do also post all these videos onto YouTube after we do it. So it's the exact same thing. We say, like, this is being recorded right now. And if you just look up Pyrotech Systems on YouTube, you can see a lot of our old training videos. This one will get added too. It might not make it on there today. It might not be till tomorrow that it makes it on there. But if you've ever missed one or you want to go back and revisit one because you're like, I remember we talked about it, but I don't remember what the outcome was, they're available on YouTube, so y'all can watch them whenever you need to.
All right, that sounds good. So that means everybody needs to subscribe.
Yeah. Like, subscribe, hit the bell notification, whatever else they say. All right, how's everybody else feeling about this? Do you kind of feel like you're getting a start of an understanding of what the open and closed switches do and how they work in relation to being in resting state and not resting state?
Yeah, appreciate that.
Okay, and as we keep going through this over the next few weeks, if y'all need me to kind of pause and rewind, or maybe I said something confusing, definitely feel free to ask about it. Stanley, did you have a question? I saw it looked like you were about to say something.
No, I'm good. I was just checking something out.
Okay. So yeah, as we're going, definitely pause me if you need to ask questions. There's a really good chance that if you have a question, somebody else might have it. I want to make sure that we all get this the best we can. This is going to help all of us. This each and every job site, this is going to be something you run into, whether you're dealing with the door contacts for like overhead doors or access controls, sprinkler equipment. Pretty much every single building we do has sprinklers, kitchen hoods, all these kind of things. This is a really common thing that each case that we do it with is going to be a little different. That's why I'm going to do several weeks on it, so I can get a handful of those different scenarios and actually put them here in front of the camera. My ideal situation, I'd love it if I could get a handful of y'all together at some point and actually have little stations to go around, and we could work together in the same room. And okay, so now we're going to wire up a dummy sprinkler system, or we're going to wire up this fake kitchen hood over here. This COVID stuff hasn't blown over yet, so I know we're trying to do our best to keep from assembling too many people in one place at a time. And that also costs money to get that many people together and not be working on a job site. So, stuff's going to have to kind of line up and match. but we're going to be looking for whatever ideas we can to help keep the training going. And I hope seeing this on the camera in front of you helped a little bit more than trying to see something like this on a slideshow as well.
Hey, I've made arrangements to pick up a water flow switch and a tamper switch from BMF Solutions. I just have to find somebody up in the Cypress area to pick it up.
Okay, cool. Yeah, if we get those before next Wednesday, which I don't see why we can't, I think I'm going to try to mess with the sprinkler stuff next week. I'm going to keep using that red light instead of a bell because I don't want a bell glowing off this close to my face. I'm sure y'all can understand why.
Yeah, just use the buzzer from one of them 7100 pounders.
Man, those things don't even work on those panels. All right. Well, if y'all don't have any more questions, thank y'all for being here. Y'all are free to go, and I'll see you next week. If y'all have any questions you come up with over the course of the week, feel free to send them to me. If you think of anything that you might be confused on and want us to do in these training topics, I'd love to hear from you. Send me all those ideas you got. I want to make sure that these are what y'all actually need and that we're not giving you stuff you don't need. Like I said, with that, if you don't have anything else, y'all are free to go.
See y'all. Thank you.